nice little break from microeconomics, and today we're going to look at some complex analysis. A nice, easy example of complex analysis, and probably one of my favorite integrals ever. So we're going to be looking at the integral between minus infinity and infinity. It's a terrible infinity sign of sine of x over x dx. Now, before I'd actually come across this approach, I thought that these were impossible. I thought that they used made up functions. So like the integral of cos x over x, I think is referred to as um ci of x or something like that. You may have to fact check me on this, but it's similar to when you do sort of like the indefinite integral of e to the minus x squared, right? Like this becomes the earth function. I think I don't know. I'm not too sure on that. You'll have to fact check me on that. But anyway, this one we can look at using complex analysis. So what's the very first step? A second grader could think of what we're going to do first with this interval. We are going to times it by 2. And we are going to look at it over 0 to infinity instead of the whole set. So we have 2 lots of the integral between 0 and infinity sine of x over x dx. And now we're going to evaluate this over the half plane. So we're going to draw this out. And I always draw this terribly out, so don't bash me. Let's get a straight line. Bang. Let's get another straight line from here. Let's go. We got this, we got this, we got this, we got this. Looking pretty straight. Okay. And now we're going to need one just above it. Like, imagine this is like on the line. And we're going to stop here. Cool. And as we're getting towards the origin point, we're going to want to go over. So I'm going to start labeling already. We got minus r is this point here. And we're traveling clockwise. And we're going to hit this point. We're going to call it minus epsilon. And we're going to take a little detour. And we're going to come back down here at this point epsilon and start traveling back along. And we're going to hit our point R. And this is also going to be a point little gamma. And then we're going to go back around anti-clockwise around our plane back to R. Not too well drawn, but it'll do. So we're going anti-clockwise. There we are, axes. That's a limit, no, not an image thing. And then the real line. And yeah, this one we're going to call Big Gamma. God, that's terrible. It'll have to do. Okay? So what we're doing is we're jumping around origin, taking this little detour here. And now we're going to set up our contour integral. Don't be afraid of it. Don't be afraid of it. It's one of my favorite signs in mathematics. Sean, how cool is that? I mean, come on, look at it. It's like the final boss, but it's really not. It's intimidating looking, but it's really a nice little simple boy. And all we're gonna do is add up all of our separate intervals, okay? So this is our function z. Did I even define the function z? I don't think we did. We're gonna say our function z, we're gonna let it be e to the iz over z, okay? Just some simple stuff. Sure. So our integral of the function z is going to be all of these points added up. So we're going to be looking at the integral between minus r to epsilon, like here, okay? So that's our first one. The integral between minus r to minus epsilon of f of x dx. Why did I write it like that? Why did I put the okay plus our little gamma integral here plus the integral over little gamma of f of z dz plus the integral from epsilon to r of f of x dx plus our final one, which is our big boy gamma. God, I can't draw gamma to save my life. Like, I actually just can't, though. F of z dz. Sure, this is it. And using our theorem, we know this is all equal to 0. And what we're going to try and do is find this integral, sine of x. I should probably get rid of these random points over here. They look a bit weird, don't they? Kind of loses track of what we're actually doing. Okay. We're going to try and find this by using our little analysis here. So first of all, let's look at this integral here, epsilon to r f of x dx. So let's rewrite it out. The integral from epsilon to r of f of x dx. Now, this is the integral between epsilon to r of, what did we say? E to the ix over x dx. Okay. And now we're adding to it the integral between minus r to minus epsilon. And what we're going to try and do is make these the same, sort of. Minus r to minus epsilon of e to the ix over x. Now, these are pretty much the same, right? The only difference is our bounds are flipped, and we got a minus. So we want to switch it up. So what we're going to do is we're going to say u equals minus x. Let u equal minus x. And we're going to have quite a few minuses when we do this. Du is going to be minus dx equals that. And now e to the iu over u becomes e to the minus ix over minus x. So minus the whole thing, and then you've got a minus dx. So there are quite a lot of minuses. But what's really going to happen is that you're going to have e, with all these minuses, we're going to pull one minus out, which is going to make our bounds positive, and then the other minus is going to make them switched around, and we're just going to be left with a minus in the e to the ix part, like this. That's going to be the only minus left, and now our bounds are going to be from epsilon to r. And now, look, they're very similar. So we can add these together, because we're just going to have the integral between epsilon to r of e to the ix plus e to the minus ix over x. Look familiar, guys? It's basically just your sine of x, your definition for the sine of x. What is our definition for the sine of x? Well, sine of x is the integral. No, it's fucking not. Um, what am I doing? What am I doing? What am I doing? E to the ix plus e to the minus ix all over 2i. So what are we out by? We're just out by this factor of 2i. So what we really have is 2i times the integral between 0 and infinity of sine of x over x. If we let epsilon go to 0 and r go to infinity. That's what that becomes. I should probably specify that we're doing that little step. So we just have this 2i component here. And basically, what we're aiming to do here is have this sine of x over x as one of these terms, and then have some other terms and bring them over to the right hand side so we can say the integral between minus infinity and infinity of sine of x over x equals this. That's what we're trying to do. And we've already got a 2i component here. So what's left is we got to evaluate our gammas. So we'll start with little gamma. And it's kind of annoying because it's going clockwise. So when you introduce your parameter, you're going to have to account for this. It's not going to be e to the minus t. It's going to be like e to the I pi minus t because we're going round clockwise. And so to get from epsilon back to minus epsilon, you're going to have the one of the parts having pi taking it away will bring you down to 0. Our parameter is going to be between 0 and pi, but it's going to be e to the I pi minus t instead of just e to the I t like it normally would. So our big gamma is just going to be, I'm going to use sigma for that though. Sigma of t is just going to be re to the I t. But yeah, let's just do it. Let's just do it. That's good. Okay. So zooming in here. What are we doing? The integral of little gamma of f of z dz, and this is just going to be the integral over little gamma of e to the iz of z dz. Nice and simple. And we're going to introduce our parameter. So let gamma of t equal epsilon e to the it, epsilon e to the I. No, it's going to be pi minus t. I just discussed this. And yeah, this is going to be it. Like I said, because we're going clockwise. And what we want to do is we want to differentiate our parameter. So just write gamma dot of t. And this is going to be, bring the power down. We're going to have a minus I epsilon e to the I pi minus t. Quite simple. That's an e, not an epsilon. I get so confused when doing epsilon. I'm always writing e's, and then I look back and I'm like, that should be an epsilon. So what do we have? We've just got minus I times r gamma of t, basically, right? You agree that this is just so for, oh, I didn't even specify that we're doing. So we just have that gamma of t, gamma dot of t is going to be gamma of t times minus I. So now our integral becomes the integral between 0 and pi. That's our bounds of e to the I gamma of t over I gamma of t? No, just gamma of t. Um, times minus I gamma of t. This is going to cancel with this, and then the minus I, and all we're going to be left with is minus I integral from 0 to pi of dt, which is just going to be minus I pi. And is going to be what's left, okay? So that's our little gamma evaluated. And so what we have left is our big gamma. And that one we are can just do without, because it's going anti-clockwise. So like this, f of z dz. I'm not too good at explaining these sorts of things. I kind of just like I get it, and then I can't put it into words, so to say. There'll be a mathematical way to say it, and I'm unfamiliar. Too many big boy words in maths. Like my proof here on the Euler-Mascheroni convergence that I've been doing for my paper. It's homoplicity or homogeneity or something like that, and I just call it that we're just making a sequence here and looking at it like that, and it's not the correct way to say it. And then I say we're looking at learn as an expression of these integrals as like a partial sum and finding bounds. That's what we're doing, but there's some big boy words to say what we're doing, and that's why I need to write in my paper. Ugh. Okay, so we're gonna use sigma. Sigma of t is gonna be rei to the t, nice and simple, between 0 and t and pi. Now this is all gonna go to 0. We're gonna see it go to 0. I'm gonna do it terribly, but it goes to 0. So differentiate our parameter, and we are gonna get re. No, we're not. We're gonna get ri e to the it. Am I missing anything? No. And this is gonna be I theta t theta sigma. And so our integral becomes the integral between of gamma e to the I z over z dz is gonna be the integral between 0 and pi of um e to the I sigma t all over sigma t, yes, times I sigma t dt. Okay. Now, oof, this is kind of big. It's like I integral between 0 and pi of e to the I or e to the I t dt. Kind of annoying, right? So, what's going to happen? I'm going to say it in words and then write it down. As R grows, we're going to be looking at the absolute value, and it's going to be the absolute value of the integral from 0 to pi of e to the IR, and then we have this e to the it, and we know e to the it is going to be cos t plus I sine of t, right? And you're going to split that up into two e's as e to the ir cos t and e to the minus r sine t, and we're going to say that that is less than um, the integral between 0 and pi of e to the ir cos t absolute value times e to the absolute value minus r sine t. Sorry, the absolute value of the whole exponential function. And as r goes to infinity, 0 to pi e to the minus r sine t goes to 0, and 0 to pi e to the ir cos t goes to 1. So effectively, the integral over gamma of the function is going to be e to the 1, which is 0. So it all collapses to 0 and becomes irrelevant. But I'll write it out, and I will talk. I will sing a lullaby as I do it. Um, I don't know any lullabies. Twinkle, twinkle. Oh, yeah, I can do that one. Twinkle, twinkle, little star, how I wonder what you are. I've already wrote the stuff out, right? Yeah, I have. For fuck's sake. Up above like a diamond in the sky. Twinkle, twinkle, little star, how I wonder what you are. Beautiful. Wow, that was so moving. Is it minus? Yeah, it's a minus. It's a minus. Bang, 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 bada bing, bada boom. As all goes to infinity, angle between 0 and pi of e to the minus r sine t goes to 0. And the 0 to pi e to the ir cos t goes to 1. So just e to the 1, so 0. So the integral over big gamma, well, that's a better gamma. It's still not great, but it's slightly better. F of z dz is just 0. Brilliant. Cool. So now we can add up what is left of our contours. And so we had that, what was it? Our contour integral That's a bad one, actually. That'll do. Of two equals 2i of the integral between 0 and infinity of sine x over x dx. No, don't need the dx. Sine of x over x minus I pi, which was left, plus 0, as we just got, equals 0. This is a fun bit. It nicely collapses now. We can say 2i integral between 0 and infinity sine of x over x equals I pi. Divide through, and the integral between 0 and infinity of sine of x over x equals I pi over 2i, which is just going to be I cancels, bang bang, pi over 2. How nice is that? So the integral, our scary looking integral of sine x over x is just going to be proper, dx equals pi over 2. Bang, bang, bang. And so that is contour integration using complex analysis here to find our residues. And residues, I don't even know what's going on today. I genuinely don't know. But that's some nice little analysis there. Hope you guys did enjoy, and I will see you in the next one.